The cosmic scale can't but amaze. Against the background of some planets, the Earth appears as a barely visible rocky fragment, and next to some stars the Sun may seem just a tiny spark in the icy emptiness. And today, we're going on a journey to some of the most spectacular cosmic objects known to date. We'll start out from the majestic Saturn, surrounded by its imposing rings. We'll fly over its raging atmosphere, make our way through swarms of icy shards, and encounter the mysterious Titan. And then, in a matter of a few moments, we'll travel hundreds of light years to see a ring system dozens of times larger, called super-saturn. Then we will make acquaintance of the unpredictable and dangerous Betelgeuse, a dying star that could explode into an all-consuming supernova at any moment. Leaving it behind, we will head towards the majestic red giant Stephenson 2-18, one of the largest stars in our galaxy. And after that we'll visit another fading giant, which falls into a rare class of carbon stars. Leaving the Milky Way, we'll travel to the amazing and mysterious Andromeda, the closest large galaxy to us. After exploring its glittering star arms and impenetrable nebulae, we'll move on to one of the greatest voids in the universe, whose origins are still shrouded in mystery. Let's get ready, and we begin. Kosmo. The first in outer space. Approximately 100 million years ago, a large, icy satellite approached Saturn too closely. The gas giant's extremely powerful tidal forces shattered it into trillions of small bits. Obeying the overwhelming physical laws, these bits gradually spread out, embracing the planet in a primary ring. It was roughly 1,000 times more massive than Saturn's today's rings. Millions of years have passed since the time of the disaster. Since then, some part of the destroyed satellite's fragments was swallowed up by Saturn without a trace. Other debris bombarded the surfaces of its multiple satellites, or else left the environs of the gas giant altogether. This is one of the most well-grounded scientific hypotheses today that account for the origins and evolution of Saturn's rings. Even after hundreds of years of observations, this tremendous structure in space still hides a lot of secrets. Saturn's rings do not have a clear-cut border. The width of their visible part is about as much as 280,000 kilometers, although there are thinnest clusters of dust and rarefied gas beyond these borders. These structures' diameter reaches 16 million kilometers, according to some estimates, although they cannot be seen from the Earth on account of their extremely low density. In spite of the impressive dimensions, the total mass of the ring system is quite small by space standards and is estimated at 3 × 10⁻19 kilograms, which is about 2,000 times lighter than the Moon. Solid objects account for only 3% or so of the structure's overall volume, with the rest filled with rarefied gas and cosmic dust. The disk surrounding Saturn is conventionally divided into several large rings. However, a rather powerful optical telescope will reveal each of them to be clearly made up of a large number of thin circles separated by narrow gaps. These gaps form due to the gravitational influence of both the planet itself and its many satellites. Some of them are as much as several hundred kilometers wide. Even though Saturn's disk reflects several times more sunlight than the gas giant itself, some rings are next to impossible to see. For example, the D ring, the closest to the planet, which consists of tiniest water ice crystals and frozen methane. Its upper border is posited to be located 16,500 kilometers above the planet's conventional surface. As for its inner part, the ring has no clear-cut border and gradually fuses with Saturn's atmosphere. Next to it is the brighter and more massive C ring, which is approximately 17,500 kilometers wide. It is comprised of space objects measuring up to 2 meters and which make up just 0.033% of the disk's overall mass. The brightest and most outstanding part of the disk is located further and is designated the B ring. It begins roughly 34,000 kilometers above the surface of the gas giant, and its width reaches 25,000 kilometers. The thickness of the larger part of the ring does not measure over 5 to 10 meters, while its outer part forms a vertical rim towering up to 2.5 kilometers high. The outermost visible ring of Saturn begins 64,000 kilometers above the planet's surface. It is roughly 14,600 kilometers wide, harboring not only comparatively large ice bits of 10 meters and more, but some satellites as well, such as Pan, Daphnis and others. The existence of such large objects may prove the theory of ring formation following the destruction of the ice satellite. Alternatively, they may have formed at a later time as a result of smaller fragments colliding and merging. Beyond this part of the disk, there lie the almost unobservable F, G and D rings, which formed from cosmic dust and rarefied gas. It goes without saying that most of Saturn's large satellites actively interact with the rings. Traveling as far as 179,000 kilometers away to the region of the so-called E ring, the celestial body dubbed Enceladus is to be found. With a diameter measuring just 500 kilometers, it does not qualify as one of the gas giant's largest satellites, but it stands out for other reasons. The point is that Enceladus is one of the few celestial bodies in our system where there are clear manifestations of cryovolcanic activity. Analysis of the observed emissions proves that there is an ocean of liquid water under its surface. Mathematical modeling shows that its temperature measures from 45 degrees Celsius below zero in the upper layers to 0 degrees at the bottom. Due to a high content of dissolved salts and ammonia, the ocean does not freeze over even in sub-zero temperatures, with the icy shield about 2 kilometers thick covering and thermally insulating it. The celestial body's surface temperature is about 75 Kelvin or 198 degrees Celsius below zero. Its atmosphere is extremely rarefied and is 91% water vapor. Other elements making it up are nitrogen, carbon dioxide and methane. Powerful geysers that erupt from time to time through cracks in the icy crust of the satellite regularly supply its atmosphere with chemical elements, but the celestial body's weak gravity is not enough to prevent the atmosphere from floating away. The upper region of the atmosphere is constantly losing some amount of particles that go to sustain the E ring. On the other hand, Enceladus constantly captures material from the space around it, thus ensuring its peculiar chemical balance. It is known that geyser activity of this celestial object depends on its orbital movement. It is likely that Saturn's tidal forces deform the satellite's icy shield, causing it to crack in multiple places and to erupt. It is also known that the cryogeyser's emissions contain elaborate organic molecules, which may mean that the conditions in the subsurface ocean may hypothetically be favorable for the genesis of biological life. Also, the gas giant's fifth largest and most massive satellite, Tethys, can be seen approximately 300,000 kilometers away from it. It is peculiar for sharing the same orbit with two other celestial objects, Telesto and Calypso. They are located at the so-called stable Lagrange points, with Telesto 60 degrees ahead of the main satellite in its movement along the orbit, while Calypso, on the contrary, lags 60 degrees behind. Unlike the massive spherical Tethys, these celestial bodies are not that large and are irregular in shape. They measure roughly 20 to 30 kilometers in diameter, with their overall mass just several trillion tons, which is modest by space standards. Interestingly, modeling shows that Calypso and Telesto could not have originally formed in the same orbit with a more massive body following it, which means that they arrived to join it at a much later time. As for Tethys, it is a celestial object with a diameter measuring about 1,060 kilometers, made up of mostly water ice, with some rocky impurities in its composition. The most outstanding feature of its relief is the giant impact crater Odysseus. Its diameter measures around 450 kilometers, which is about twice as small as the diameter of Tethys itself. Its depth reaches as far down as 3 kilometers. There is also an easily noticeable chasm of enormous proportions on the satellite's surface, which is called the Ithaca Chasma. It is as long as about 2,000 kilometers. That is about a third of the celestial body's circumference and as much as 100 kilometers wide. As for its depth, it ranges from 3,000 to 5,000 meters, and the bottom is pockmarked with a great number of craters and minor irregularities of the surface. According to one of the theories about it, the Ithaca Chasm formed as a result of Tethys's subsurface ocean freezing over. On turning into ice, the water expanded in size and erupted through the satellite's outer crust. Another assumption about the chasm has to do with the Odysseus crater. It is thought that the impact waves traveled across the entire surface of the satellite and caused a powerful resonance around its circumference. As a result, Tethys's crust cracked, forming this incredibly large chasm. Still further from Saturn, there lies its largest satellite, Titan, which also boasts quite a number of highly unusual features. With a diameter measuring 5,152 kilometers, it is in fact the second largest satellite in the solar system, with Ganymede holding the first place. It is also remarkable for being 5.5% bigger than Mercury. Titan is also the only satellite in the solar system with a dense atmosphere and bodies of liquid on its surface. Since Titan lies quite far from the Sun, the temperature of this celestial body is quite low, at around 94 Kelvin or 180 degrees Celsius below zero. Having said that, in spite of its comparatively small mass, Titan is capable of sustaining an atmosphere which is 1.5 times denser than that of the Earth. Nitrogen accounts for over 98% of the atmosphere's chemical composition, with methane and other gases making up the rest. Exposed to solar wind, nitrogen and hydrocarbon compounds in the atmosphere's upper layers transform into more complex organic substances, which subsequently slowly settle on Titan's surface. Due to the impermeable hydrocarbon smog, the satellite's surface is unobservable in the optical range. According to the most plausible model of Titan's inner structure, there is a massive rocky core at its center, with a diameter measuring about 3,400 kilometers. It is embedded in a thick layer of exceptionally dense ice, which forms the bottom of a cool salty ocean containing up to 10% of dissolved ammonia. It is buried under a crust of water ice mixed with methane hydrate, which is many kilometers thick. In temperatures as low as that, The ice has properties identical to those of a solid substance and forms mountain ridges and elevations on the surface. As for lowlands and chasms, they are filled with lakes of liquid ethane and other hydrocarbons. Solar wind and Saturn's extremely powerful magnetic field constantly strip Titan of its atmosphere. However, its internal processes keep replenishing it, so the process of losing it may take billions upon billions of years. When the Sun hits the red giant phase, it will be capable of vaporizing the hydrocarbon haze and melt the eternal ices on Titan. After this, the satellite will become a more favorable place for the genesis of life. However, it will not happen for a while yet. Of course, Saturn's system does not end there. "434 light-years from Earth. A surprising object, informally called super-Saturn, is located 4 astronomical units away from a young Sun-like star. It is a brown dwarf, or a large gas giant, 20 times as heavy as Jupiter. Observations show it to be a young planet, about 15 to 16 million years old, which is still forming. Most of its atmosphere consists of hydrogen and helium, with a massive metallic core in its depths. This object is spun by a system of rings, like Saturn's but much larger. The transit method revealed at least 37 distinct rings, with the largest one's outer radius measuring about 0.6 astronomical units. This is comparable to the size of Venus's orbit, and about 640 times the radius of Saturn's rings. According to calculations, the total mass of the circumplanetary disk is bigger than the mass of the Earth, and its behavior manifests signs of randomness. Mathematical modeling shows that such structures are not stable and gradually disintegrate. Some of the objects making them up lose velocity and fall to the central planet, while others, on the contrary, accelerate and leave the disk forever. However, this process is greatly extended in time and may take several 100 million years. Also, a large rupture with a radius of about 0.4 astronomical units was detected in the system of rings, which is considered indirect evidence of the existence of an exosatellite in this region, about 80% the mass of the Earth. According to current understanding of the physics of space objects, it is a kind of object capable of clearing its orbit of small debris, forming a wide rupture in the ring structure. In addition, observations suggest the presence of at least 2 more celestial bodies, with a mass of each of about 30% that of the Earth, and located at a distance of about 0.25 astronomical units from the center of the brown dwarf. Just like it is the case with the large planets known to us, it can be assumed that a total of several hundred exosatellites, including rather massive ones, may be located within the gravitational influence of the central object. A simulation of such a system, including radiation from a parent star, heat flow from a giant planet, and tidal influences, shows that the temperature of the celestial bodies making it up could approach comfortable values. One can only imagine how enchanting the night sky would be from the surface of such an exosatellite. At this distance, the brown dwarf occupies 70 times as much space in the sky as the full moon, and its soft glow can dispel the darkness and turn the night into a misty twilight. Instead of the star-spangled canopy, the planet's sky is crisscrossed by vast swathes of light from horizon to horizon. At the same time, the tidal forces of a nearby massive body could provoke multiple eruptions on the satellite's surface, and its hypothetical ocean could slam the land with giant waves. The width of a tidal zone under such conditions could reach hundreds of kilometers, making it a unique climatic zone, something like a cross between land and the ocean floor. Still, it should be mentioned that such structures tend to be unstable and change their appearance quite quickly beyond recognition. It is difficult to say how much longer we'll be able to admire the giant rings and what they will look like in millions of years. The end of 2019. Astronomical observatories report a sudden decrease in the luminosity of the star known as Betelgeuse. Observations show that its luminosity dropped to 36% of the standard value within a matter of a couple of months. Some scientists are talking about an upcoming supernova, which will be the brightest object in the night sky. Disturbingly, the gamma-ray flow emitted by the explosion is thought to be potentially dangerous for life on our planet. April 2020. Astronomers assure the general public that Betelgeuse has recovered its luminosity to the standard value. It may still go supernova at any moment, but there is no way to predict this event with any degree of certainty. Assumptions about reasons for such anomalous fading are put forward. According to the most popular hypothesis, it was caused by a giant cloud of gas and dust ejected by Betelgeuse in the direction of the Sun very recently. June 2021. The assumption is confirmed by data from Earth-based telescopes. Astronomers keep observing the object, while astrophysicists model out the processes occurring in its interior. Before we attempt to get to the bottom of what was taking place, it's a good idea to be aware of what Betelgeuse is like. This object falls into the category of red supergiants and is in the final stage of its life cycle according to today's theory of stellar evolution. With its luminosity and radius constantly changing, its outer layers are highly unstable. The star regularly emits millions of tons of scorching gas into space, and this forms gargantuan prominences. As they cool off, they contribute to the gas nebula surrounding Betelgeuse. The star's mass is around 17 times that of the Sun, and its diameter has by now been gauged only roughly at 700 to 880 times that of the Sun. Hypothetically, if Betelgeuse were to be placed in the center of our system, it would swallow up all the planets as far as Mars, as well as most of the asteroid belt. It should be mentioned that the star has no clearly defined edge because its outer layers are extremely rarefied. Besides, the object is shrouded in a gargantuan gas nebula made up of cooled-off prominences or protuberances and particles of stellar wind. At the same time, the density of stellar matter on the conventional edges of the star is only slightly higher than that of the nebula. Betelgeuse is a remarkably bright star. Its minimal luminosity is 90,000 times higher than that of the Sun, while its maximal luminosity is a staggering 150,000 times higher. Interestingly, the star's temperature is not that great considering it ranges from 3,400 to 3,800 Kelvin, which corresponds to the red spectral band. There are barely predictable processes running in the unstable outer layers of the star that are capable of elaborately changing the object's luminosity. The main pulsation period of the star is approximately 420 days, but less distinct cycles of longer and smaller periods can be singled out too. Besides, unpredictable flares and dimming of the star can be observed from time to time. Because this star is so unstable, it is extremely difficult to calculate the distance between us. According to the estimates offered by the Coriolis satellite in 2020, the distance between the Sun and Betelgeuse is anything from 500 to 650 light-years. According to today's notions of stellar evolution, Betelgeuse would have formed around 8.5 million years ago, and its original mass wouldn't have been over 20 solar masses. Its life cycle would have started in a giant cloud of interstellar gas that would have been gradually compressed and heated up by gravity forces. That is how the protostar, the progenitor of Betelgeuse, was born. At a certain point, the temperature and pressure in its interior reached high enough values to unleash a chain reaction of hydrogen transforming into helium. Moments later, the thermonuclear interaction consumed the entire astronomical body, and a new star flared up in the night sky. This is how the longest period in the life of any star begins, the main sequence stage. Throughout this time, merging of hydrogen atoms' nuclei that produce helium is the main energy source for them. Admittedly, the heavier a star, the faster this process runs. Life expectancy of massive stars like Betelgeuse is a measly several million years, whereas red dwarfs remain active for billions of years. Either way, over 90% of a star's life passes in the main sequence stage. gradually accumulating. Helium is drawn to the object's center to form a helium core. What happens to the star next depends almost entirely on its mass. For example, stars with masses not over 20% that of the Sun do not go supernova at the end of their existence, unlike more massive stars. Having eventually run out of almost all of their hydrogen, they slowly turn into blue dwarfs, hot and comparatively small astronomical objects. However, the minimal time it takes to complete this transformation is around 1 trillion years, which is 72 times the assumed age of the universe, which is why it is doubtful that any blue dwarf will be discovered today. After hydrogen supplies are depleted, thermonuclear reactions in the star will stop and it will become a white dwarf made up of 99% of helium. Ahead are trillions of years of slow fading and cooling until a tepid black dwarf is left instead, which is barely visible through telescopes. If an object's mass lies in the range from 0.2 to 8 solar masses, its evolution goes through more elaborate processes. Helium, which is produced as a result of thermonuclear reactions, adds to the star's core while gravity forces compress it and heat it up more and more. At a certain point, there occurs a reaction of helium nuclei merging, which produces carbon. The star begins to expand, its radius grows as well, and the temperature of the outer layers drops. In this case, the object turns into a red giant or subgiant. Comparatively light stars with masses not exceeding 50% that of the Sun cannot sustain conditions necessary for the chain reaction of helium and carbon. Transformations like these are quite irregular in such objects. As for heavier objects, reactions occurring in the star's core may run longer and produce not only carbon and oxygen, but also heavier elements, like nickel and iron. Eventually, the star sheds its outer layers and what is left is a white dwarf enveloped in a planetary nebula. If the initial mass of the original star wasn't more than half that of the Sun, it will mostly be made up of helium, with just a small ratio of heavier elements in its composition. If, on the other hand, the star was heavier than that, the white dwarf would be mostly made up of oxygen and carbon. However, with the original star having been heavy enough, it will include neon, magnesium and even iron. Evolution of massive objects has its laws. The heavier a star, the more massive its core. With the mass of a star 8 or more times that of the Sun, its core might get over the so-called Chandrasekhar limit, which is 1.4 times the mass of the Sun. In this case, forces of internal electromagnetic repulsion are not strong enough to compensate for gravitational compression. It takes a few seconds for the core to shrink, pulling the outer layers in its wake. The exceptionally powerful compression heats up the core to temperatures of hundreds of millions Kelvin and literally crams electrons into atoms' nuclei. This turns part of the electrons into neutrons and produces great amounts of neutrinos. Even a dense material like that is not able to hold back the most elusive particle in the universe. In a few seconds' time, neutrinos break away from the collapsing star and escape, taking some thermal energy with them. As a result, the star experiences extremely powerful internal pressure, as the closely packed protons repel each other with a great force. That is why the core goes on to expand as rapidly as it shrank a few seconds previously, and this produces a tremendous shockwave in the material surrounding it. As a result, a tremendously powerful explosion occurs, which is capable of hurling the star's outer layers enormous distances away. Its flames can unleash reactions that are impossible anywhere else. That is how heavy elements are produced, like gold, lead or uranium. The nebula formed as a byproduct gradually cools off and disperses to form separate clouds, which are later compressed by gravity forces and transform into new stars and planets. Where the star has been, there remains a tiny but extremely heavy object referred to as a neutron star. If the original star's mass was over 18 to 20 times that of the Sun, on explosion its core is supposed to shrink to form a black hole, a bizarre object that distorts time and space around it. Mathematical modeling shows that particularly large stars with masses over 100 times the mass of the Sun may hypothetically be destroyed by the blast completely. In this case, all the material they are made up of will be scattered by the shockwave many light years around, or else be transformed into extremely powerful electromagnetic radiation. An electromagnetic impulse from a supernova is capable of covering hundreds of light years. At first, the radiation is characterized by incredible force, annihilating all living things on its way. However, with the covered distance growing, the density of the flow decreases and the lethal rays gradually disperse in space. Estimates show that a star similar to Betelgeuse may be a threat to anything within the radius of up to 100 light-years. It is absolutely impossible to tell when this star will go supernova, but it is likely to do so in the nearest 100,000 years. According to some estimates, Betelgeuse may flare up as brightly as the full moon. The dying star will remain the dominating object in our night sky for a while, and then will gradually fade. The object will not be visible to the naked eye anymore, and only the most powerful telescopes will be able to distinguish the radiation emitted by the tiny neutron star. If the mass of Betelgeuse is actually bigger than is assumed now, it may leave a black hole after going supernova. In this scenario, the energy flare will be by far smaller and the sight much less impressive. Either way, there is no threat to the Earth. Betelgeuse lies too far away from the solar system, and a gamma-ray flare that will accompany the supernova will not cause us any harm. The material ejected by the explosion will reach the environs of our system only in 6 million years. Its speed is estimated to be around 13 km per second and will be thwarted by solar wind before getting as far as the inner areas of the system. Until a short time ago, it was UY Scuti that used to be considered the largest star known to mankind for a long while. Located 9,500 light-years away from the Sun, the star is so staggeringly enormous that it would cover areas beyond Jupiter's orbit were it placed in the center of the solar system. Its radius may reach 1,900 those of the Sun, and its volume may be over 5 billion times that of the Sun. However, recently a new giant has claimed the title of the largest star in the known universe. It is known as Stephenson 2-18, or RSGC 2-18. The star lies approximately 20,000 light-years away from the Sun and is part of the open cluster Stephenson 2, although according to some scientists, this space object should not be associated with the Stephenson cluster, as it wouldn't be accurate. Either way, Stephenson 2-18 is located in the Scutum constellation and continues to bear its original name. The star itself was catalogued in the All-Sky database back in the 1990s, but giant clouds of cosmic dust largely interfered with observation of the star clusters in the Scutum constellation, obscuring them from any observer anxious to find out more. Only in 2020 were scientists able to acquire data about its size, and the information proved to be astonishing. According to some estimates, the radius of Stephenson 2-18 may reach up to 1.5 billion kilometers, which is 10 times the distance from our Earth to the Sun, or 2,150 times the radius of the Sun. This means that the supergiant's volume should be about 10 billion times that of the Sun. Placed in the center of the solar system, Stephenson 2-18 would easily swallow up Saturn, along with all of its rings and moons, to say nothing of the terrestrial planets. Interestingly, it would take light almost 8.5 hours to travel the length of this gigantic star's equator. This is the same time it takes sunlight to reach Pluto at the remotest point of its orbit. The supergiant's luminosity is estimated to reach 440,000 times that of the Sun, although its surface temperature is comparatively low at about 3,200 Kelvin. This is about 2 times as little as that of the Sun, and corresponds to the red band of the light spectrum. This is the reason why Stephenson 2-18 falls into the category of red supergiants. Also, this relatively low temperature implies that most of the star's radiation is in the visible and thermal spectra, with amounts of deathly ultraviolet and X-ray types of radiation rather negligible in comparison. It may seem strange that in spite of its impressive dimensions and sufficient luminosity, Stephenson 2-18 cannot be seen from the Earth with the naked eye. But this has to do with its low surface temperature as well as clouds of stardust and gas shrouding the giant star, thus concealing it from observers on our Earth. They absorb and disperse the star's light, and this poses difficulties for studying the object. The mass of Stephenson 2-18 still remains to be gauged. However, supposing its inner makeup is similar to that of UY Scuti and other supergiants, it should be anything within 20 solar masses. If it is the case, the average density of supergiants like that must be extremely low and almost equal to the density of the Earth's atmosphere at a height of about 90 kilometers above the sea level. That is practically on the border with space. It is really amazing that thermonuclear energy, that is the kind of energy that gives a glow to a star, is still sustained in such conditions. Supergiant sizes are so mind-boggling that these objects are hardly steady. Most of them are variable in terms of their luminosity, and as a rule this variability is unpredictable. No wonder, as the overwhelming majority of supergiants are in the final stages of their life cycles, which means that they may go supernova literally at any moment. According to the contemporary scientific concepts of stellar evolution, it is stars with original masses from 10 to 40 that of the Sun that qualify to become red supergiants at a later stage of their existence. Thermonuclear reactions in their interior rapidly burn out all hydrogen, thus turning it into helium. After that, fusion reactions of helium, carbon, oxygen and lithium become the chief energy source of the star. Life expectancy of stars of this kind is comparatively short, just a few million years. As it evolves, the prospective supergiant rapidly expands in size and loses its mass on account of strong solar wind. Clouds of stardust and gas surrounding the original star are quickly absorbed by the new star, which keeps swelling way beyond its original size at an astonishing rate. However, its own solar wind creates a new nebula around the star. On account of the short lifespan of this kind of star, no planets can realistically originate in this nebula. Eventually, the supergiant explodes. Following the supernova or even hypernova event, the outer layers of the star are hurled away and then gradually cool off, forming a nebula. As for the former core, it becomes either a neutron star or a black hole depending on its mass. By the way, feel free to see our previous videos about dwarf stars and supernovae. A hypernova event is accompanied by a high-energy X-ray burst, powerful enough to eliminate any life within the radius of several light years. Luckily for us and the Earth, all supergiants identified by scientists so far lie considerably further than that, so we seem to be safe from those. Due to active radiation of charged particles, the rotation of stars of this type gradually slows down, and eventually their outer layers practically grind to a halt. The core of the star, meanwhile, continues to rotate quite unabated, and there may be a substantial difference between the speed of the core and that of the outer layer. Taking into consideration the high luminosity, low temperature and impressive dimensions, on balance, it is safe to assume that the habitable zone of Stephenson 2-18 should be really huge. Its middle should lie approximately 663 astronomical units away from the star's center. In other words, 20 times the distance from the center of the Sun to Pluto's orbit. And as for the area of the habitable zone, it is expected to be 1 billion times that of the Sun. Scientists do admit of the possibility of the existence of planetary systems around supergiants. But what with these stars' short lifespan and unstable conditions, the chances are almost negligible. At any rate, no confirmed exoplanets have so far been discovered in the environs of one. Stephenson 2-18 lies so far away that its light travels to our Earth for 20,000 years. For all we know, at this very moment its core might be shrinking to form an extremely dense neutron star,
with red-hot shards of outer layers flying away in all directions to become part of ice-cold space. But mankind will be able to find this out only in a very distant future. "650 light-years away from the Earth, there lies IRC plus 10-16, a majestic star also known as CW Leonis. Its radius at its pulsation peak may reach 560 times that of the Sun, which is about 2.6 times the distance from the Earth to our parent star. With CW Leonis hypothetically placed in the middle of our system, all the planets as far as Mars would find themselves under its surface, which would even brush the inner boundary of the asteroid belt. Incidentally, the star's mass is not that great, roughly 1.5 to 4 solar masses. Its surface temperature is just 2300 Kelvin or about 2000 degrees Celsius. But due to its impressive dimensions, the star emits on average 8,500 times more energy than our Sun. Like any other red giant, CW Leonis is in its final life stage. Its age hasn't been defined precisely, but it is estimated to be several billion years. It is assumed that in its salad days, CW Leonis was a white-blue star with a mass 3 to 5 times that of the Sun. However, by 1 billion years ago, a great part of the celestial body's hydrogen had burned out and transformed into helium. Slowly settling in the star's center, the helium ousted all the remaining hydrogen and formed a scorching hot core which did not participate in any thermonuclear reactions. This process, typical for all stars whose mass is close to that of the Sun, is the starting point for a star's transformation into a red giant. The star's inner pressure causes it to expand to great proportions, which renders the outer layers more rarefied and unstable. The space object's diameter grows to be dozens of times greater, with its color gradually assuming a blood-red hue. A thermonuclear reaction still takes place in the star's depths, which causes the pressure and temperature of the stellar plasma to increase. At a certain point, this unleashes a chain reaction of nuclear fusion, where helium nuclei are transformed into carbon. This is the so-called helium flash. It is a complex, multi-level physical process that dramatically transforms the star's inner structure. With its core incredibly heating up, its outer layers, on the contrary, cool off and darken. There are currently great amounts of carbon in CW Leonis, but its mass is insufficient to hit the next level of nucleosynthesis. As a result, the thermonuclear combustion in the object's interior becomes unstable. The stellar matter gradually cools off and shrinks under the influence of gravitation. This heats up the star's interior again, and the reaction is unleashed with a new force. After receiving a new portion of thermal energy, the stellar matter expands again, and the combustion dies down. It is assumed that this cyclic process underlies the occasional changes of the star's luminosity. CW Leonis has a 649-day pulsation cycle, and with the luminosity at its peak is 11,300 times brighter than the Sun. With the luminosity at its lowest, meanwhile, the object emits 6,250 times more energy than the Sun. At the moment of contraction, the upper layers of stellar matter partly detach themselves from the star. This forms a carbon-oxygen gas nebula that the star is enveloped in. According to some estimates, CW Leonis loses 4 times 10 to the power of 22 tons of material every year on account of this process, an amount approximately 7 times the mass of the Earth. Observations show that the circumstellar nebula is not less than 69,000 years old, and its mass is about 1.5 times that of the Sun. As for its size, it reaches 84,000 astronomical units. The nebula has an elaborate structure with bulges and pockets of gas, as well as half arcs and irregular rings. It is posited that these formations appeared due to magnetic activity and stellar wind generated by the unstable star close by. The chemical composition of the cloud CW Leonis is shrouded in is of great interest to explorers. Spectral analysis data reveals it to contain around 70 different chemical compounds, for example carbon dioxide, water and ammonia, to name but a few. There are also quite a lot of elements from the upper part of Mendeleev's periodic table, right down to iron. CW Leonis may have had planets in the past, but they appear to have been swallowed up early on at the stage of expansion. In any event, years of observations did not reveal distinct traces of their existence in the past. What was registered was subtle changes in the star's orbit back in 1994, and more recently in 2017, mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. Some small red dwarf orbiting the giant could well account for these phenomena, although attempts to detect its radiation have so far been unsuccessful. This could be due to the nebula close by, which disperses and reflects the energy flow from sources of light located nearby. This phenomenon camouflages any objects in the immediate environs and prevents them from being accurately recognized. The mass of CW Leonis's hypothetical stellar companion is assumed to be definitely smaller than that of the Sun, and it should take it approximately 100 years to complete a full orbit around the giant. Another outstanding feature is the comparatively high water content in the star's environs and envelope. At first, it was posited that the star would melt and swallow up icy comets as it expanded. However, observations carried out in 2009 showed the temperature of some spectral lines to reach 1000 Kelvin, which is possible only on condition that water vapor forms actually in the upper layers of the giant. This fact did not fit in the model of red giant's structure accepted at the time, according to which all oxygen and stellar matter necessary for water synthesis must be used up completely to produce carbon monoxide. A new hypothesis was put forward to account for the witnessed phenomena, which stated that molecules of silicon oxides and carbon are destroyed by a powerful ultraviolet radiation. After that, the released oxygen reacts with hydrogen and there forms scorching hot water vapor. The weakness of this hypothesis is in the failure to account for the source of ultraviolet radiation. Reactions like that may occur only in rather high temperatures, that is, within stellar matter. However, it is practically impervious to cosmic rays. This paradox may be explained by yet another assumption. Since the star is unstable, large ruptures and low-density areas occasionally occur on its surface, where ultraviolet radiation is not blocked out that effectively. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons. Enormous though this figure may seem, in fact, water accounts for just around 1/1000th of the star's overall mass. According to today's notions of stellar evolution, being a red giant, CW Leonis is in its autumn years now. It will deplete its stellar fuel in the next 10 to 30,000 years, after which it will discard its outer layers following a powerful explosion. It will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, and its temperature will reach several million degrees in the first seconds after the transformation. However, with no energy source, it is destined to slowly and irrevocably fade in the course of billions of years to follow. Eventually, the celestial body will be almost invisible against a background of cosmic emptiness when it becomes a mysterious black dwarf. But this will not happen anytime soon. The shockwave and the mind-boggling temperature in the epicenter will generate new elements that are not to be found in a star's interior. For example, uranium, gold and lead. They will later become part of new celestial objects. Millions of years later yet, radioactive decay will heat the planet's interiors, melt the ice, and saturate the oceans with microelements, thus creating conditions for the genesis of life. The universe is constantly evolving, and global cataclysms and destruction are an inalienable part of this process. But at the end of every storm, there are fresh rays of light. The year 1885. The planet Earth. The attention of all astronomers on the planet is focused on an amazing astronomical event. A remarkably bright flare in the region of the Andromeda Nebula briefly eclipses the nearest stars with its radiance. This amazing supernova is dubbed as Andromeda, and its anomalous parameters baffle astronomers for a long time. But just 6 months later, the star rapidly dims and soon disappears from the sky forever. Unfortunately, at the time of the flare, generally accepted notions about the structure of the universe were far from those of today. At that time, astronomers were not yet able to measure distances to cosmic bodies, so the bright spot in the constellation Andromeda, also known as object M31, was considered an ordinary reflection nebula on the outskirts of the Milky Way. Meanwhile, with the advent of new, more powerful telescopes and the development of space technology, the situation gradually changed. As soon as in the 1920s, observations by Edwin Hubble and other astronomers proved that the Andromeda Nebula is a different galaxy, much like the Milky Way. About a century has passed since then, and science has moved far ahead. It is currently known that the Andromeda Galaxy has a spiral structure and comprises about 1 trillion stars. As for its diameter, it exceeds 150,000 light-years, and its mass is relatively small and ranges from 800 billion to 1.5 trillion solar masses, about the same as the Milky Way. This is thought to be the case due to the abundance of red dwarfs and less dark matter in its composition. Like all spiral galaxies, Andromeda has a massive nucleus at its center, made up of millions of closely spaced stars. Its radiance is so great that it dazzles observation instruments, making it impossible to distinguish individual stars. On account of this, the remnants of the 1885 supernova, known as S Andromeda, have long been impossible to trace, although surviving records clearly indicate that it exploded near the center of the galaxy. It was only in 1988, 103 years after the legendary flare, that a small nebula was detected at a small distance from the nucleus, a dark spot standing out against the background of the dazzling central region. With the help of spectral analysis and proper motion modeling, it was firmly established that it is a remnant of S Andromeda. Thus, this cosmic object became the first supernova detected outside the Milky Way. Careful study of the central part of Andromeda will clearly reveal its unique difference from other spiral galaxies. It is an unusual double nucleus, the origin of which is not yet fully understood. The brighter and larger part is located slightly away from the geometric center of the galaxy, and is a giant supercluster of many bright stars with a total size of about 7 light-years. The second part, on the other hand, is closer to the center and is noticeably dimmer and smaller, with a diameter of about 1.3 light-years. It is assumed that this region hides inside a supermassive black hole about 50 million times heavier than the Sun. The nature of such a strange phenomenon remains a subject of scientific debate. According to some assumptions, in the distant past, M31 absorbed and scattered a rather large satellite galaxy, and the bright region is a remnant of its core. According to other hypotheses, the center of Andromeda still has a single structure. However, it is separated by a band of opaque dust, creating an unusual optical effect. Due to the remoteness and inconvenient location of the galaxy in space, it is still impossible to collect enough data to confirm these hypotheses one way or another. Meanwhile, as we continue traveling through the central region of Andromeda, you can also spot one of the most mysterious objects in this galaxy. Here is its tongue-twisting name on your screens. The key feature of this celestial body is that it is almost impossible to see even in the most powerful optical telescope. However, everything changes if you use X-rays. In this part of the spectrum, this star is the brightest point in the galaxy. Observations show that the object is a system made up of two components, one of which is a low-mass neutron star. Its radius is only a few dozen kilometers, and it completes a full turn around its axis roughly every 3 seconds. The second star of the system is a larger object. Although it is relatively dim, it's most likely a red giant. Calculations show that the total mass of both components is not more than 3 solar masses, and the distance between them is very small. Every 4 hours, the neutron star is eclipsed by the other star, and this causes its luminosity to sharply drop, to recover its previous values later. It is also very likely that due to the small distance between the stars, the neutron star is gradually absorbing its companion, which is why its mass is constantly growing. According to calculations, this process will last several tens of millions of years, and eventually, the second star will be torn apart by tidal forces and turn into a bright and hot ring-like nebula. Incidentally, this amazing object is only one of the many stars densely surrounding Andromeda's core. Together they form a massive bulge with a diameter of about 12,000 light-years, which has a noticeably elongated shape. Also, M31 has a pronounced bar, which however faces us with its narrow side and so is almost invisible to the observer on the Earth. According to calculations, the bar's length measures about 17,000 light-years, with a width about 6,500 light-years. In total, about 30% of the Andromeda galaxy's entire mass is concentrated in its central part. While we are gradually moving away, we can see that the edges of the bar serve as the basis for 2 giant spiral arms, majestic coils encompassing the center of the galaxy. At the same time, there are darker gaps between them, whose width is significantly larger than those in the Milky Way, reaching 13,000 light-years. Calculations show that the Andromeda arms contain about 56% of the galaxy's stellar mass, as well as some dark matter. Under the influence of gravity, interstellar dust and gas concentrate in the arms, forming numerous stellar nurseries, regions where new stars are born. Over time, these gas and dust clouds evolve into open clusters and associations containing a great variety of young stars. Their light is reflected and scattered by cosmic nebulae, endowing the galactic disk with an incredible, shimmering palette of colors. And in one of these clusters, there is a remarkable star dubbed AE Andromeda. It is one of the brightest stars in the galaxy and is a hot blue giant whose luminosity varies without any apparent pattern. Such objects are known as luminous blue variables and are extremely rare. Currently, only a few dozen are known. Because of the extremely high temperature and pressure, the outer layers of AE Andromeda are constantly in a state of unstable equilibrium, and the processes running in the interior of the star are largely chaotic and unpredictable. From time to time, streams of red-hot plasma collide with each other, generating extremely bright flares and enhancing the luminosity of the object by several dozen times. Hypothetically, the most powerful of them can increase the brightness of the star several million times. Such a phenomenon is called a supernova imposter and may occur at any time. Measuring the parameters of such a star what with its instability and remote location is an extremely difficult task. Nevertheless, with the help of modern ultra-precise telescopes, it turned out that the mass of A Andromeda lies in the range from 50 to 120 solar masses, and the radius at the peak of pulsations measures about 55 times the radius of our Sun, which is only slightly smaller than the orbit of Mercury. At the same time, its surface temperature is close to 20,000 Kelvin, and its luminosity is 500 to 700,000 times greater than that of the Sun. Just like all blue giants, A Andromeda generates remarkably strong stellar wind, whose speed, according to calculations, can reach 100 kilometers per second. Because of this, the object loses about 2 quadrillion tons of matter per second, which means that its mass decreases annually by an amount similar to 10 planets such as Earth. However, for such a large star, it is almost imperceptible, because A Andromeda will complete its evolution much sooner than the losses incurred from the stellar wind will reach at least 0.1% of its mass. The fact is that despite its age of 2 million years, which is mere seconds by space standards, A Andromeda has already completed most of its life cycle. According to calculations, within the next million years, the star will go supernova, leaving behind a black hole surrounded by a vast gas and dust nebula. Speaking about the age of the stars, one cannot help noticing that they are scattered unevenly throughout the galaxy. Thus we can look into Andromeda's past and observe how it was being formed. The oldest stars, some 11 to 13 billion years old, are concentrated in the central part of the galaxy. In contrast, the disk and spiral arms mostly contain younger stars, ones formed about 3 to 4 billion years ago. Here, the numerous stellar nurseries contain pretty much baby stars, born only a few million years ago, which is practically seconds by space standards. This means that in the first stage of its evolution, M31 was much smaller in size, and its shape resembled an ellipse. Also, by analyzing the parameters of individual stars in Andromeda, it is possible to define an important, but at the same time rather conditional concept known as galactic habitable zone. It is believed that the concentration of stars in the central part of Andromeda, as well as the high level of radiation and unstable orbits of potential exoplanets, make this zone unfavorable for the genesis of life. At the same time, distant planetary systems located at the periphery of the galaxy are too poor in heavy elements, which implies that there are not that many Earth-like planets. Therefore, only the intermediate region of the galaxy can be considered hypothetically habitable. It is in this kind of zone, at a distance of about several tens of thousands of light-years from the center of the galaxy, that a small faint object known as Mega ML7 is located. It is a red giant, with a relatively small mass of about 50% that of the Sun. In 1999, thanks to a fortunate coincidence, astronomers were able to record the phenomenon of microlensing, during which they were able to study this inconspicuous and distant space body in more detail. The results of these measurements helped determine the mass and spectrum of the star, as well as the temperature of its surface, which was about 3,700 Kelvin. But the most important observation was the rhythmic deviation of the trajectory of the star from the main direction of its movement. Such oscillations are considered a sign of a possible presence of a fairly massive companion. The hypothetical object was dubbed Mega ML7b and is now considered a potential exoplanet. If the existence of this celestial body is confirmed, it will be the first exoplanet in the history of astronomy to be discovered outside the Milky Way. Information about this object is still rather scant, but calculations show that it is highly likely to be a gas giant, with a mass of about 6.3 times that of Jupiter. There are also reports that this system is likely to be as diverse as our own in terms of chemical elements. which means that there is a good chance of finding a variety of planet types within its boundaries. Not only gas giants, but also rocky celestial bodies similar to Earth. When we observe the Andromeda galaxy, another striking feature that becomes immediately apparent is the great multitude of star clusters and associations, whose number is much bigger than in the Milky Way. In total, about 460 globular star clusters and about 10,000 open clusters are known to exist in M31, as well as several dozen large star associations. Some of them are concentrated in the center of the galaxy, others are scattered in the halo, and still other ones have settled right in its spiral arms. And one of the largest and most noticeable structures is NGC 206, a cluster located almost at the very edge of the galactic disk. Previously, this association was considered a globular cluster, but now, due to its size, it has received a higher status and is called a stellar association. In this region of space, with a radius of about 200 light-years, roughly 300 extremely bright stars and countless less noticeable ones are concentrated, with a total mass of about 200,000 solar masses. Their overall luminosity is so great that the association is visible from Earth in an amateur telescope, along with the core and arms of the galaxy. According to observations, NGC 206 formed after a merger of at least two large gas and dust nebulae separated by a dark band of interstellar dust. The age of one of them is about 10 million years. The other is noticeably older, having formed about 50 million years ago. The single giant nebula became a point of gravitational attraction for interstellar gas, which led to the formation of a great area of star formation. Over time, some of its stars will dissipate in the surrounding space, with the rest forming a large globular cluster. The galactic disk M31 contains many such formations, and not all of them originally formed within its boundaries. It is assumed that many large stellar associations are the remnants of major cosmic catastrophes of the past. According to calculations, throughout its entire existence, Andromeda absorbed more than 100 satellite galaxies. Some of them dissolved without a trace, while others turned into giant stellar streams. The collision with the object known to us as M32 may be considered the greatest. This compact elliptical galaxy is located above the Andromeda disk, only 17,000 light-years away from it. Its diameter is about 8,000 light-years, and considering its small size, the galaxy has a rather big mass, about 1 billion solar masses. In the center of M32, there is a supermassive black hole about 2.5 million times heavier than our star, which is surprising for such a compact object. In fact, M32 is just a remnant of a much larger galaxy that survived the Great Catastrophe. According to data from the Spitzer Orbiting Telescope, about 800 million years ago, a large satellite galaxy pierced Andromeda's disk at high speed, leaving a gigantic hole in one of the spiral arms. During this collision, M32 lost most of its stars, and it is unlikely to be restored to its former appearance. It is assumed that it could have been a full elliptical galaxy, or a small spiral galaxy, of which only the central part remains. In addition to M32, Andromeda has about 30 satellite galaxies connected to it by invisible gravitational threads. The brightest and largest of them is M110, which has a diameter of about 15,000 light-years. Most of the rest fall into the category of dwarf spherical galaxies and are located within 1 million light-years. Nevertheless, together they form the Andromeda subgroup, which is part of the local group. Its other members are the Milky Way and its surroundings, as well as the Triangulum galaxy and some other objects. Inexorable gravitational forces are gradually pulling the local group towards a single center. That is why the Andromeda galaxy is rapidly moving in our direction, covering over 300 kilometers every second. Just imagine what a stupendous portion of our cultural heritage would never have been around. A great number of myths and legends have to do with the stars. It goes without saying that any travels to other stellar systems would be out of the question. Even a few light years is an overwhelming distance for man even at this point of our scientific progress. As for covering several 100 million light years, the mere thought is no more than just a fanciful dream. It would take man inventing extremely powerful and advanced telescopes to be able to see that the Sun was not the only star in our universe. But would they ever be invented? There is no way of finding it out, especially if we take into account the fact that it is stars themselves that have always been a powerful stimulus for man to try to get to the bottom of the nature of the universe. Chances are that a bleak, dark sky would never have fascinated people, and as a result, no modern devices and equipment for observing space would ever have been developed. In one of our previous videos, I've already told you about gargantuan cosmic voids, or else I take it you would have heard about these. Voids are large-scale expanses of space that are almost or completely devoid of galaxies or galaxy clusters. These enormous objects take up about 50% of the observable universe. The average void measures approximately 40 megaparsec, or 130 million light-years. However, the diameter of champion voids may reach several 100 million or even a billion light-years. These extra-large voids are rather predictably referred to as supervoids. The density of matter in these regions is much less than in other areas of the universe and accounts for less than 10% of the average density in meta-galaxy. Voids are the largest formations among the large-scale structures of the universe, on a par with galactic filaments or thread-like formations. Cosmology today explains their existence by diversity of matter when the universe was formed. One of the largest voids ever discovered is the VENATICI supervoid. Spotted in 1988, this supervoid is the second largest void known to science today. With a diameter measuring a staggering 300 to 400 megaparsec, or a billion light-years, the VENATICI supervoid is located 1.5 billion light-years away from our Earth. Interestingly, just 17 galaxy clusters are located in this area of mind-boggling dimensions, and this is extremely little for such an incredibly enormous expanse of space. All the 17 clusters are gathered within a comparatively small area by space standards, namely within a measly 150 million light-years. If any gravitational interaction between them does take place, more advanced technologies are called for to detect it. The diameter of the VENATICI supervoid accounts for approximately 1% of that of the observable universe. It could easily accommodate 10,000 galaxies identical to the Milky Way in terms of dimensions. Who knows, perhaps there are life forms on a planet hidden somewhere in these 17 clusters. However, there is no way light from our Sun will ever reach those parts, and any interaction with potential inhabitants of those parts of the universe is effectively out of the question. Now, what is a billion light-years? The history of multicellular life forms on our Earth, starting from primitive coelenterate animals, counts just over 800 million years. In other words, life on our planet evolved from colonies of protozoans to humans in the time a photon traveled from one edge of the supervoid to the other. It takes some stars less time to complete their entire life cycle, from getting born to going supernova or finishing life in an alternative way. Actually covering this distance in a spaceship, romantic as it is, sounds like a recklessly eccentric idea. In order to understand what space inside a void is like, you have to think of a deep physical vacuum. It may contain interstellar gas clouds, independent star clusters, or even galaxies, but most of the supervoid contains nothing. The name is self-explanatory. Of course, space expanses are for the most part vacuum. Just to give you an idea about the proportions, there is a cubic centimeter of dense stellar matter to thousands of cubic kilometers of space. But even this space is not completely empty. A mark of 100 kilometers above ground is the accepted limit of the Earth's atmosphere. At this height, the atmospheric pressure is so small that it becomes comparable to that of solar wind. However, there is no clearly defined transition to space, and even several hundred kilometers above the Earth's surface, there can be found an extremely small amount of gas molecules from our atmosphere. Seemingly negligible, these molecules still manage to slow down artificial satellites orbiting our planet. As a result, many of them have to regularly adjust their orbit in order not to lose their momentum and not to have to get back to Earth prematurely. Gas concentration is much lower the further we are from a planet. But even beyond our solar system and away from any star or planet, there will always be at least a few molecules of hydrogen in every cubic centimeter of space. In addition to that, there will be solar wind in space, a current of high-energy subatomic particles emitted by the Sun. And of course, other things have to be reckoned with, like radiation of distant stars, relict radiation and neutrinos, subatomic particles particularly hard to detect. The vacuum inside the void is deep to such a point that there is less than half a molecule of matter for every cubic centimeter of space. Besides, all sources of radiation are so remote from it that the density of their radiation is quite negligible compared to relict radiation. As a result, all that remains is undetectable neutrinos and the cosmic microwave background. As I've mentioned before, there is something else to be found inside the incredibly vast expanses of the void apart from deep vacuum. There are also clouds of interstellar gas, the future nursery for stars and galaxies. Secondly, dark matter is supposed to be found inside supervoids, but today's methods of detection are hardly adequate for studying it. It should be noted that the overwhelming majority of voids detected so far are located hundreds of millions of light-years away from the solar system. In essence, what we are observing now is the distant past of these formations. Only one void lies relatively close to the local group of galaxies, among them the Milky Way, and is referred to as the local void. Its diameter measures approximately 180 million light-years, and the distance between the Sun and the void's center is about 90 million light-years. The Betelgeuse void is another large formation about 700 million light-years away from the Sun. The diameter of this void measures approximately 330 million light-years, which is about 0.35% of the diameter of the observable universe. The Betelgeuse void was discovered in 1981 by a group of scientists headed by Robert Kirshner, with theoretical arguments in favor of the existence of supervoids having been formulated 20 years previously. The supervoid is thought to have been formed as a result of several smaller voids blending together. Just 60 galaxies have been pinpointed inside the Betelgeuse void by now, although such staggering expanses could easily have accommodated about 2,000. Speaking about the most mysterious void in the universe, it lies 3 billion light-years away from the Sun. It is known as the CMB cold spot or the Eridanus supervoid. This supervoid is a champion even by supervoid standards. With a diameter measuring 1.8 billion light-years, it may easily have accommodated 18,000 galaxies similar to the Milky Way. The Eridanus supervoid's temperature is from 70 to 150 degrees microkelvin colder than the average CMB temperature of the universe. Today's theory of the universe's origin cannot give a definite explanation to this fact. This so did not fit into the accepted theory in cosmology that at first the measurements were dismissed as faulty and the equipment was blamed. Only after several years of scrupulous measurement were the readings finally accepted. A great number of explanations, including rather extravagant ones, were offered concerning the strange temperature properties. One hypothesis has it that the anomalously low cosmic microwave background in the Eridanus supervoid is a result of the influence of supermassive chunks of dark energy. According to another hypothesis, this area is what is left of another universe that had existed before ours. Be it as it may, there is disappointingly no definite answer yet.
Some cosmic structures are so vast that their size can hardly be appreciated by the human mind. These large-scale formations play a decisive role in shaping the universe, which means that their study can give us the key to understanding its past and future. Every atom of our world is part of the gigantic mechanism of the all-consuming cosmos. Its study may take many generations, but ultimately, it will allow us to find out more about our place in the infinite universe. And let's keep in touch.